Okay, this is section 8.2, Ionic Bonding. Now, what we're going to find in chapter 8 is that we're going to primarily talk about covalent bonding, which we'll look more at in section 3. But for right now, we're going to talk about ionic bonding. And the idea here is the following. Imagine that we want to make a compound. We want to take potassium and we want to react it with an iodine atom. And we want to form potassium iodide. Now, if you think about it, potassium is a metal. Iodine is a nonmetal. So our compound here is an ionic compound. That's generally observed, is that if you react, generally, if you react a metal with a nonmetal, you'll get an ionic compound. We'll talk more about that later. But the question then is, how do we describe this in terms of our Lewis symbols? Potassium has the Lewis dot symbol, K with a dot, right? One valence electron. It's in group 1A, one valence electron. The iodine has a Lewis dot symbol, 1, 2, 3, 4, 5, 6, 7. It's in group 7A. So the question then is, what's going on in terms of the product, in terms of Lewis dot symbols? So here's what I'm going to do. I'm going to think of this as two half reactions. So in the first half reaction, K is getting converted into K plus an electron. So our Lewis dot symbol would be K goes to K, but remember, it's an ion, so in terms of Lewis dot symbols, we draw brackets around it. Okay, so there's your K plus an electron. Now let's do the same thing for the iodine. Half reaction. Iodine, which has 7 dots, 2, 3, 4, 5, 6, 7, is going to gain an electron. So it now has 8 electrons in its valence shell. It's negatively charged, so we write it like this. Okay? So there's our two half reactions in terms of Lewis dot symbols. There's this one, and there's this one. Now, what we're going to do is we're going to describe ionic bonding as simply a electrostatic attraction. Simple electrostatic attraction. Do you remember what that means? What that means is that if you have something that is positively charged, and then you have something that's negatively charged, and they are relatively close to each other, they will experience an energy of attraction or a force of attraction. Okay? So the force of attraction is proportional to the amount of positive charge there is times the amount of negative charge that there is divided by the distance between them squared. Okay? This is called Coulomb's law. It's not written as an equation. If we were doing calculations in the physics course, we would actually calculate forces, but we're just going to say proportionalities, and so we're not going to worry about the actual quantitative calculation. But what this shows us is that positively and negatively charged particles are attracted to each other, and that attraction is proportional to the amount of charge they have, multiplied together, divided by the distance squared. Now be careful, because there is a related equation that says that the energy of attraction is proportional to the negative of the amount of positive charge times the amount of negative charge divided by the distance. Not distance squared, just distance. Okay, so these are related quantities. Force and energy are related, but they're not the same. In this discussion, we're focusing primarily on force of attraction as opposed to the energy of attraction. We go back and forth when we analyze chemistry. So in the case of potassium iodide's up there, really what's happening is the potassium ion is just simply attracted to the iodine ion, right? Those are both ions. And they're just attracted to each other because they have opposite charges. And so the amount of attraction that they have is dependent on how much positive charge the cation has. So if it has more positive charge, like +2 or +3, that number is larger, times the amount of negative charge that the anion has, -1, -2, -3, divided by their distance, which in a sense is how big they are. The bigger they are, the further their centers are from each other. Okay? So those are the three variables in determining how much energy of attraction, how much force of attraction that the two of them have. Now here's the problem. Potassium, if you take potassium and iodine, they will form potassium iodide exothermically, meaning they will release energy. It's negative delta H. Exothermic. This is what we would call a spontaneous process, meaning if you take potassium and iodine and you put them together, you're definitely going to get the product Ki, and it's going to release energy. The problem is if you go through a calculation of how much energy it takes to remove this electron, that's called ionization energy. And the amount of energy it takes to gain an electron here, to give us right there, and you add them together, it's not exothermic. It's endothermic. So there's something wrong here. The amount of energy it takes to take the electron off the potassium, the energy it takes to give you the extra electron to iodine, doesn't add up to an exothermic process. So what's going on? Well, one way of approaching this is to introduce the idea of lattice energy. So I'm going to introduce this now. Okay. So lattice energy is the following idea. If you take a look at this picture here at the top, this is lithium iodide, sodium iodide, and potassium iodide, three different substances. See how the sizes of the ions vary? They're different sizes. The size of an ion depends on the nucleus and it depends on the electrons. Okay? So these have different sizes. And if you take a look at the lithium iodide, look at how the distances are. The size of the lithium iodide, the lithium ion is 0.76 angstroms. The size of the iodide ion is 2.2 angstroms. If you look at the sodium iodide, the sodium ion is bigger than the lithium ion, and the potassium ion is bigger than the sodium ion. So what happens is those distances are changing. Coming back to this equation, the distance, the force of attraction is right here, right? Or here if you want to think of it in terms of energy, okay? So that is important. But now let's come back to this picture again. If you take a look at the second picture down at the bottom, what it shows you is that in fact the lithium ion, these ions we're talking about, whatever they are, whichever ones we're talking about, are not just attracted to one ion. They're attracted to lots of ions. Ionic compounds do not form molecules. They form matrices or lattices. It's called a lattice, a group of ions, a cluster, a large cluster of ions attracted to each other. So what happens is, the reason ionic compounds form is because all of these ions cluster together and there's lots of attractive forces and lots of attractive energies. Overall, the sum of all the attractive energies is called the lattice energy. So each iodide ion is surrounded by a cluster of potassium ions. All those energies are attractive, and all together we call it the lattice energy. So lattice energy is the reason that ionic compounds form. It's not just the attraction of two ions, it's the attraction of a large number of ions, okay? Lattice energy. Now let me show you some measured or calculated, I should say calculated, because lattice energies really cannot be measured. They have to be calculated for various compounds. For lithium fluoride, the lattice energy is 1,017 kilojoules per mole. So those are the sum attractive energies of all of the ions in lithium fluoride. So coming back over here, these are for lithium iodide on the far left, right there, okay? Lithium chloride, 860. Lithium bromide, 787. Lithium iodide, 732. Notice the pattern. It's decreasing as you go down. The reason is the charges of those ions are all the same. Lithium is always +1, fluoride's -1, chloride's -1, bromide's -1, so forth and so on. But they get bigger. The fluoride ion is smaller than a chloride ion, so the average distance between these ions gets bigger, so the energy gets smaller. Okay? So if you come back to this figure up here, see how they have the lattice energies at the bottom? The largest is the lithium iodide, LiI, 732. Then sodium iodide, 686. Then potassium iodide, 632. The reason it's getting smaller as you go left to right is because the anion is getting bigger. Okay? I'm sorry, the cation is getting bigger. The lithium ion is smaller than a sodium ion, which is smaller than a potassium ion. So as the ion gets bigger, the distances get larger, the attractive energies get smaller. Okay? Now let's take a look further down in this table. If you look at the bottom, MgCl2, Na2O, and MgO. See how the lattice energies are getting bigger? Okay. The biggest one is MgO at 3890. The reason for that is that the lattice energy also depends on, let's come back up here. The lattice energy also depends on the amount of charge. So if the charge gets bigger, the energy gets bigger, right? If this energy gets bigger, if this charge gets bigger, this energy gets bigger. So it's also proportional to the amount of charge. So what happens is, when you look at this table at the bottom at MgO, the magnesium ion is +2. The oxygen ion, oxide ion, is -2. +2 and -2, that's a large charge. You multiply those together, you get large lattice energy. The Na2O, the sodium is +1, the oxide is -2, so you have a -2. That's a big charge, so you have a large lattice energy. But not as big as MgO, because in MgO, both ions are +2 or -2. They both have a charge of 2. Okay? There you go. Now notice on the far right, the melting point. The melting point is affected by the lattice energy. MgO down at the bottom has the largest melting point. The melting point is the temperature at which something melts, turns into a liquid. So in a sense, you're separating the ions, allowing them to move around each other with the melting point. So the reason that MgO has the largest melting point is because it has the greatest lattice energy, the greatest attractive energy. Whereas LiF is a lot smaller because the charges are smaller, the lattice energy is smaller, so it has a lower melting point, easier to move them away from each other. Okay? Now, the lattice energy is positive, but I want to show you something called the Born-Haber Cycle. This is described in this section. The Born-Haber Cycle is a way to calculate the lattice energy. The lattice energy cannot be measured directly. The lattice energy is the amount of energy it takes to go from the compound. So for example, this, to convert it into the ions. Okay, it's the energy associated for that. Okay. So the question is, how do you measure that? You can't really measure that very easily. Okay. So the way it's done is through what's called the Born-Haber Cycle. You take all of these measured delta H values and you add them together according to Hess's law. And then that will give you the lattice energy. So for sodium chloride, it comes out to 787 kilojoules per mole. It's a very clever process. And it's done by taking delta H values that you can measure and then combining. Remember what happens with Hess's law? If you add the equations and you get an overall equation that you're looking for, there you go. So this can't be measured directly. Can't measure it directly. So what you do is you take all of these 5 reactions and you combine them. And so take a look at what happens. The sodium solid cancels. The sodium gas cancels. The chlorine gas cancels. The electrons cancel. The 1/2 Cl2, I'm sorry, I made a mistake down here. There we go. Okay, so we got that one, we got that one. Okay, so 1/2 Cl2 gas cancels. And then you're just left, it's kind of messy here, right? But you're left with essentially NaCl solid is converted into Na plus gas and Cl minus gas. So that's this equation right there. So you can't measure it, but you can calculate it according to Hess's law, and then that gives you the energy right there. So Hess's law determines the lattice energy, and the lattice energy right there will give you essentially the attractive energy of all these ions together in the form of clusters like it's shown down here at the bottom. Okay.